Professor Taoufik Hmidi from New York University in Abu Dhabi and Rennes University in France. Taoufik défend une habilitation à diriger les recherches en problème de Cauchy pour quelques équations d'évolution in 2008 and a PhD in mathematics in 2003 at École Polytechnique France. From 2001 to 2004, he teach on École Polytechnique France, and from 2004 to 2020, he was associate professor at University Rennes 1, France, and from 2020 to 2022, a visiting professor at the New York University in Abu Dhabi. And since September 23, he has a position of a professor at New York University in Abu Dhabi. The research topics of Taoufik are fluid dynamics, vortex dynamics, critical global local well-posedness theory, and compressible and implicit limits. He also worked on Schrödinger equations, blow-up theory, profile decomposition, Schrödinger equation with a singular potential, and on free probability, on unitary Brownian motion, spectral distribution, Jacobi process. Thank you, Taoufik, for accepting our invitation. And you have between 45 and 50 minutes to expose your work. Thank you, Taoufik.
Okay, so thank you, Nabil. Thank you for all the organizer for this nice and kind invitation. So my talk today will be around some aspects in fluid dynamics, and especially around some self-organized structure that they can emerge in turbulent flows. But before that, I think I need to make some motivation, because we can encounter this structure around us. For example, we have a nice here video. I can share with you this video. This video. No, before that, yeah. So I have essentially two. Here I will discuss two important phenomena. The first one is that we can observe in Saturn, what we call Saturn hexagon, this one, the first one here. And this is a big storm, and this storm has 6 sides, and this storm is rotating uniformly around its center, and the size of this storm is very huge. For example, each side is around 13,000 kilometers, and you can imagine this huge structure rotating uniformly. So this is a rigid periodic motion. And this will be connected to the first part of my talk. And the second part of my talk will be connected to what we call the leapfrogging. And this phenomena was documented around more than 150 years ago. And let me share with you this video about this leapfrogging, and you can maybe appreciate what we can see in 3-dimensional case for Euler equation related to the dynamics of rings. So here we have two. We can find this video on YouTube. So there is some simulation, and you can find it there. So we can see that we have 2 tubes, and so this is in dimension 3. So you have 2 tubes. There are 2 rings, and you see that they are starting to make a dance. So the rear ring will contract and accelerate, and it will slide inside the front one, and the front one will slow down, and so on. So this is this motion, what we call the leapfrogging phenomenon. And this is typed in dimension 3. And in dimension 2, we can find something similar. So this will be connected to the second part of my talk, to understand, to explore this leapfrogging for Euler equation in dimension 2, not in dimension 3. And we have some similarity between the first one and the second one. The first one is periodic in time. The second one is periodic in time in the translating frame. But the difference between them is the first one is rigid body motion, so we don't change the shape. However, the second one, the leapfrogging, this periodic motion, but we start to change the shape. And from mathematical point of view, we have big difference how to analyze them, and we'll see that the first one is connected to bifurcation theory. However, the second one will be connected to KM theory. So let me start with at least explain in general this kind of problems that can be encountered in dynamical system, not only in PDEs, but it can be found, for example, in finite dimensional dynamical system. And this is the situation. So imagine that we have a dynamical system. X is your state, which depends in time, and x dot is the derivative in time, and this will be given by some vector field evaluated at this point x. And your vector field could be finite dimension vector field or infinite dimension vector field if you want to discuss PDEs. Now assume that we can find some equilibrium or stationary solution. So here stationary solution means that your solution is independent in time. And if you insert in this equation, so this means that your state is a zero of your vector field. So Vx bar is zero. So x bar is a stationary state. And this is what we learn for ODEs when we start with equilibria. We want to see the phase portrait around. If we can find something interesting, for example, we can think about periodic solution. Can you find periodic solution around this stationary solution? And this is exactly what is connected to what I discussed before about this the rigid body motion vortex or this leapfrogging. This is to explore what happens around some specific equilibrium. So this is the main topic that we can discuss this kind of things, and we'll see after that. Now we will specify the model. I will discuss and switch to PDEs. And I will remind you in short quickly Euler equation. So this is the first maybe PDE that yes, you have some.
Je pense que c'est juste. Je vais couper un micro, ok.
So here this is Euler equation, and basically this is a fundamental equation coming from classical mechanics. So we can imagine that the fluid is formed by some mesoscopic particles, and they will evolve according to Newtonian law. So we can recognize in the first part here, this is what we call the covariant derivative. So this is the acceleration of your particle. And the second one here, this is the force acting in your particle. And we assume here, this is a big assumption that the force is conservative. So it is a gradient of a scalar function that we call the pressure. And this is the internal pressure. V is the velocity field. So V depends in time and in space. So X is in RD. So D could be 2 or 3. And we arrive in RD. So this is the first equation, and we see that we have two unknowns. We have the velocity field and we have the pressure. And in order to close your system, we need another constraint. And the second constraint is what we call the incompressibility of your fluid. So the fluid is incompressible, and in mathematical terms, this means that the divergence of V is zero. And now we look for Cauchy problem. We start initially with some state V0, and we want to track the evolution of your equation, if we can find solution and so on. And this is basically one of the main questions that we can encounter in PDEs when we have evolution equation. We start with initial configuration, and you want to see if we can generate solution or not. And as you know, this will depend on the function space where we have to put your initial state V0 and so on. I will not discuss really this part, but just to make a short comment that we can generate classical solution here in subvolume space, provide that your regularity is sufficiently large. So S is the regularity should be greater than the dimension over 2 plus 1. Okay. And here, just to say something, that the pressure, according to divergence is 0, we can recover the pressure from the velocity field, because when you you apply the divergence to the first equation, and the divergence will commute with the derivative in time here. So since we assume that the velocity is incompressible, so this will disappear. And we'll end up with this elliptic equation that will govern the pressure. So the Laplacian of the pressure got the divergence with the gradient of the Laplacian, and you find the divergence of V gradient of V. From this, we can, if you prescribe or you give the velocity field and you assume that you have sufficient decay at infinity, then we can inverse this Laplacian and we can recover the pressure from the velocity. Okay. So this is, in short, Euler equation in any dimension. Now we'll switch to dimension 2 because dimension 2 is very specific, as I will see. And to see the difference between dimension 2 and dimension 3, we have to move to what we call the vorticity. So the vorticity, and this was discovered by Helmholtz in 1858. He formulated the motion laws of the vorticity. But what is the vorticity in dimension 3 is the curl of the velocity field. And if you take this operator curl and you implement to the velocity equation here, you'll find the vorticity equation. And this is the vorticity equation. So you have two parts, essentially two parts in this vorticity equation. The first part is the transport part. So we transport the vorticity. And the second one is the stretching term. Okay. And in dimension 2, this is very specific. In dimension 2, what does it mean? Dimension 2, so it means that we don't vary with respect to the third variable. And this can be a good, for example, in dimension in our atmosphere at the scaling of the Earth, we can maybe neglect the height of your fluid and just to see that this will have only horizontal layers, and we can write the equation as a two-dimensional equation. So in this case, the vorticity will be given by the scalar function, depending on two variable x1 and x2, and it will point in the vertical direction 0, 0, 1. And this scalar function here now will satisfy this transport equation. So this means that the stretching term will disappear, and this is the main difference between dimension 2 and dimension 3. Dimension 2, the stretching term, which is a quadratic term, will disappear, and we end up only with the transport equation governing the vorticity. And from this now we can say many things. So just here to link the velocity field to the vorticity, this is Biot-Savart law. Biot-Savart law, when we give you the distribution of the vorticity, we can recover the velocity according to Biot-Savart law. And now, from this transport equation, we can find many conservation laws, and one of them will play a central role in the global theory. This is the L infinity bound of the vorticity. So this is transport equation. So the omega L infinity, at least at the formal level, is conserved. So the L infinity norm is conserved. And now this is the main quantity that we need in order to show that the classical solution would be global in time. In dimension 3, we don't know. We know only that classical solutions are locally well posed. In dimension 2, we know more that classical solutions are global in time. This is not really what I want to explore with you. Is what we want to explore with you is this emergence of ordered structure. So let's see for this two-dimensional case, if you can find some stationary solution. This is what we know by X bar when we have dynamical system. Can you find a stationary solution for this transport equation? It seems that Euler equation is highly rich, and you can find huge family of stationary solutions, and one of them is given by radial shapes. So imagine that we start with the take a function f. So f is the radial function. And if you start with the vorticity with this radial shape, this will generate a stationary solution. So you see that we have at least one-dimensional space that we can form in order to generate this stationary solution. So we have a big family of stationary solution. And if you want at least to recover a good, well-posed theory, we need to say, at least at this level, that F is bound and compactly support. If you are in this configuration, we can show that we have unique solution starting from this state. So we have only one, so which is exactly the stationary solution. Okay, now, so this is the first thing. So we have identified the class of stationary solution. Now, if we come back to this general framework, can we find periodic solution around this stationary solution? So as infinite dimensional space. And this is basically what we want to explore with you, and we'll distinguish between two different structures. So the question is to find time periodic solution around stationary solution. So the first one is to look to rigid time periodic motion. And for us, what does it mean? Means that there is no change of shape. So the shape is the same. And in this particular case, we'll simply focus on rotating solutions. So rotating solutions about the origin mean that we have this and that. So the vorticity or the solution will be described by this, the initial value, omega 0. And here just to rotate the points. So this means that your vorticity will be generated by rotating solutions with this frequency omega. And this is similar to what we have mentioned before for Saturn hexagon. Okay, this is periodic motion, the shape is the same. Now the second one is non-rigid time periodic solution is to see if you can find a profile omega 0 such that, and the time t, so that after some t, capital T, we come back to the original state. It could be rigid or non-rigid, and this will be similar to this leapfrogging phenomenon, because in the translating frame we'll see later that we can find a rigid non-periodic solution, and this is much more challenging compared to the first case of rigid time periodic solution. Okay, here I will specify the discussion for two families. In principle, I have three families. The first one is vortex patches. I will explain more what does it mean vortex patch, but just maybe to give you an insight about the structure is simply to say that the vorticity is distributed uniformly in some regions. So we put 1, 0, and you have some interface, this one. And this will be very, very specific structure. We'll see that this kind of structure will be preserved in time, and we can transform the motion to the evolution of the boundary. So this is the easiest case. And the second one, which is much more delicate, is non-uniform vortices, because we said that if we start with radial shape, this is stationary solution. Can we generate periodic solution around? But this is much more delicate, this one. Because the phase space is much more larger, not compared to the vortex patch. We have only one interface, and we can simply explore with the contour dynamics what happens. But when we move to non-uniform vortices, we get some of the phase space is much more large. But we have some partial results. So you will not get the time to discuss the second point. But the third one will be one of the interesting, I think, topic that I want to stress here is the point vortex system, and this will be connected to the second point here. So the first one, vortex patch, will be connected to the rigid time periodic solution, and the third one will be connected to non-rigid time periodic solution. Okay, so to be more precise, maybe so let's move to this vortex patch and say some results around this topic, how to find periodic solutions and so on. So what does it mean of vortex patch? As I mentioned before, this means that we start initially with the characteristic function of some domain D. So we take a domain D in the complex plane. So this will mean at t equal to 0. We start with some domain D, and the vortex is 1, 0. Okay, this uniform distribution, and we want to track the evolution after some t greater than 0, what happens. So what we expect is that your shape will be deformed, but the area is conserved. So this boundary will envelope or will surround some volume, some area, and this area will be conserved here in time. This is the divergence-free velocity field. But the dynamics of the boundary now is much more delicate. Okay, so we transform now the PDEs in this particular case. We start with the PDEs, which is the vorticity equation. And when we specify this structure in the vortex patch form, the vortice is described by the characteristic function of another domain dt, and we can write an equation of the boundary. So this domain D we can parameterize by some gamma here, and we can find an integral differential equation governing this parameterization gamma. This is the Lagrangian parameterization of the boundary, and this exactly the time evolution of your parameterization. It sounds to be nonlinear equation and non-local. So nonlinear because your parameterization appears here inside the log, and non-local because we integrate. Okay, maybe one of the interesting results in this topic is to see when we start with a smooth boundary, is it true that later in the future the boundary will keep the same regularity? And this was answered by Jean-Yves Chomin in 1993, who said that if we start with a boundary which is more than C1 plus epsilon, this Holder space, then at any time we keep the same regress. So there is no any loss of regularity, and this is a global result, not a local global result persistence. Okay, this is not exactly what I want to explore for you, just to say that we have different things around this topic, but I want to focus on the rigid motion, if we can find some specific structure. Now let me say something on these rotating patches. So rotating patches or rotating solution in the patch form mean that now your domain will start to rotate uniformly. So we want to see if we can find a domain D, this one, so that at any time your domain dt will be described by this pure rotation. And here to fix the center of rotation, we fix it to the origin in order to make the analysis much more simple, but you can take any point. But since Euler equation is invariant by translation, we can shift and move to 0. So this is the constraints. We start with an evolution equation, which is the Vortician, and we want to see if we can find some structure with this extra constraint. And if you insert now in the Vortician equation, this is what you find. You find that V0, which is the velocity coming from the domain D by Biot-Savart law, minus omega x perp. X perp is simply to take the vector x and to rotate with an angle pi over 2. And this relative velocity, this blue is relative velocity. So this is the velocity computed in the frame of the patch which is rotating. So this relative velocity should be dot n, the scalar product, the standard scalar product with the normal vector should be 0. So this means that this relative velocity should be tangential to the boundary. And this is a free surface problem. Okay, so this free surface, we have an extra or overdetermined problem, and we want to see if we can find some specific shapes subject to this constraint. Okay, the first elementary observation that if we take a disk, the disk is a stationary solution. We can check from the equation that this is true. This equation is satisfied. If we move to something radial shape, but this is we change the topology, the annulus, for example, 0, 1, 0. This is still a stationary solution for this one. Now we have at least two different kinds of patches. One is simply connected patch, which is this. The second one is doubly connected patch, which is an annulus with two interfaces. And we want to see if we can deform now. We can deform this disk in order to find solutions to this equation or not. And if you will succeed in this project, you can maybe expect and hope to do the same thing with the annulus. But the annulus, you have two interfaces, so we have two equations to solve. So I will come back to the annulus later and to say that when we increase the number of interfaces, you get something much more rich. So we have different nice things that will emerge in the annulus that can't be, it is completely absent with the simply connected case. Okay, so the question now, except this trivial thing, this disk and the annulus or any superposition of annulus, can we find something which is non-trivial, which is rotating uniformly? And it seems that we have, and this is the first was a discovery many years ago by Kirchhoff. Kirchhoff showed that if we take any ellipse, this ellipse will rotate uniformly, and we can compute explicitly its angular velocity. And we have to wait around 1 century later. Dim and Zabosky did some numerical simulation, and they said, okay, this is not an exception. This ellipse is not an exception. We can find more. We can find something like a rounded triangle, which will rotate uniformly. We can find something with 4 sides, like a square, 5 sides, 6 sides, maybe here, and so on. And so we see if we connect to Saturn hexagon in this framework is not an exception. Saturn hexagon is just one element of this list of rotating solutions. So this from numerical observation, but just a few years later, Burbia showed that this is true. We can prove by techniques of bifurcation the existence and the emergence of these rotating things. And this is just a diagram of bifurcation. Here, this one is exactly the rounded triangle. So we start with the disk. You can find a suitable deformation of the disk towards something with three symmetry like a triangle, and this will rotate. So this is the meaning of the first branch. We have suitable deformation of the disk towards something like triangle, and will rotate uniformly. This is for symmetry and so on. And this is this comes from bifurcation techniques, and you have to implement. You have to implement, for example, Crandall-Rabin's theorem, and we need for this purpose to linearize your equation around this trivial solution, and to understand the spectrum of your linearized operator, and to see whether these conditions, we have a list of conditions, Crandall-Rabinovich, that will tell you when they are satisfied, we can prove the emergence or the existence of such kind of solutions. Okay, so this is for the case of the simply connected. Yes, and with my collaborator in 2016, Joan de la Hoge, Juan Mateo, and Joan Verdera from Autonomous University of Barcelona, we explored the same thing with the doubly connected case. So with doubly connected case, it means that we start with the annulus 0, 1, 0. So this is stationary solution, and we can deform now. So I have two interfaces now. And we can deform the boundary in such a way that we can generate time periodic solution, rigid time periodic solutions. And so the statement is something like this. So if we fix your symmetry, M is the symmetry 3, 4, and so on. So we start from M larger than 3. So here this annulus, we have two radius here. We normalize. So the largest one is of radius 1, and the smallest one is of radius B. So this is B, and your patch is 1 inside G. Okay, so we normalize. So when we fix B now between 0 and 1, and if you fix your symmetry greater than 3 in such a way that we have this constraint, then we can find two branches. For the simply connect case, for each symmetry, you have only one branch. For the doubly connect case, if you, let's say M is 3, so you can find two different branches. Bifurcating from the annulus, and H1 will describe the threefold doubly connected state rotating uniform. Okay, so here one of the observation here that with the same symmetry you can get two branches, and for the simply connect case, since we have only one interface, for the same symmetry we have only one interface, or have only one curve. Okay, and there is more discussion on this topic. I think I have no time to discuss this. But when the two branches are sufficient close to each other, we can show that they will merge. They will merge and form a loop here. Okay, so this means that we start to rotate at two different angular values. We move, and at some point we move to the other state, which is a bifurcation from the annulus. So we form a loop. Okay, and here we see that in this case, this one is some numerical simulation. We have different configuration according to the size of the parameters, where we can explore, because we have two different branches, and we need to understand the endpoint of each branch, and the endpoint of each branch in some regimes will develop singularity, sometimes inside, sometimes outside. But this is purely numerical observation, and we have different open programmers that require maybe much more skills and sophisticated maybe analysis to explore the global branch symmetry. Okay, so this for the W connect case. Now just quickly, I want to mention that we have a lot of results during maybe the 10 years, the past 10 years. We have many things. So we can, there are different extensions. So we have different discussion on the boundary regulative. So we show that they are analytic. So when we generate these rotating solutions, so we start to explore them in a weak topology in Holder space, and after that we answer this question that they are C infinity, but after that we realize that they are analytic. So we have different authors who contribute in that direction. And the other thing is that Euler equation is one model among different transport nonlinear equation, and we can imagine to extrapolate what we know for Euler equation to this transport equation. This is what we did with my collaborators, and we have different also collaborators, especially in Spain, who worked in general surface quadratic equation, shallow water quadratic equation, and so on, 3D quasi-geostrophic. And there is another topic related to the geometry effect. Here I discussed only Euler equation, the flat space in R2, but we can imagine Euler equation in bounded domain. And one of the symmetric bound domain that we explored with my collaborator is the disk. So we imagine that Euler equation the disk. So we have this boundary effect, and we want to see the interaction between now the rotating patch with the bond, and we find different interesting behaviors. Another topic is related to quasi-periodic patches. So this is another problem coming from dynamical system. As I said before, when we have an equilibrium, I want to see around. So around. We start with periodic, but we want to see if we can find a quasi-periodic in time. What does it mean, quasi-periodic? Means that we can excite more than one frequency. For periodic solution, we have only one period, one frequency. But for quasi-periodic in time, we need to excite more if we can generate more and more. It seems that this is true for different models. And here we have a big list of some people who did interesting contribution on this topic. I think we need more and more time to say each one, the contribution of each one, but there is, I think, interesting research by these guys. Okay, so let me now move to the second part. The second part is to see if we can generate now non-rigid periodic solutions. And for this, we need to start with some limiting model. And as before, for the rigid body motion, we start with the stationary solution, which are the disk, the radial shape. And it is not easy to find a non-periodic rigid motion around. And the easiest case is to move to the point vortex system. Okay, let me say something about this. You start with Euler equation, and you assume that the vorticity is highly concentrated. So the vorticity is distributed into some Dirac masses. So I have different points now in the complex planes. Let's say Z1, Z2, Z3. So I have different Dirac mass with different circulation, gamma 1. So the circulation, gamma 2 here, gamma 3. So we have measures. So the vorticity is a measure here. And formally, at least, at this level, we can say that since omega is transported, we can get the same thing. So omega tx will be transported. So the circulation, which is the magnitude, will be the same. But the only thing that will change the center of mass of your Dirac masses. And here in this specific case, this is much more easy in some sense compared to the patches, because here we have points. For the patch, we have curves. Here we have only points, but the points will interact according to this loop. Now we have finite dimensional dynamical system. For the patch, we still get infinite dimensional dynamical system because the curve is living in infinite dimensional space. But here we have points, so they are living in finite dimensional space, and we take n points here. And this is an approximation in weak sense of Euler equation, and Helmholtz formulated this equation at the beginning to say maybe when we understand what happens for the point vortex system, it can give us more descriptions for Euler equation when we look around this Dirac mass. When we desingularize, we get something much more concentrated. This will give us some ideas. And this we will see that this is a nice dynamical system, because here it can be written into the Hamiltonian form. So we can find the Hamiltonian is the energy of your system, the particles here. And we can write the motion of your particle as a Hamiltonian system. This was discovered by Kirchhoff. And now when we have a Hamiltonian system, we want to see if the system is integrable or not. So integrable means in some sense that we can track the motion, we can describe how the particle will move, or when it starts to develop chaos. And here for Grobli Poincare show that when n is smaller than 3, this is an integrable system. When n is greater than 4, this is not integrable in general, and we still get some chaos motion. And here let me say something about small numbers of particles. Start with 2 points now. If we start with 2 points, it is not very complicated to realize that we can describe their motion in an easier way. This is integrable, but this is a rigid body motion. If we take two points, so this is the law of the 2 points, you take the difference between the 2 points, capital Z here, and you can reduce the 2 equations to only 1. And you can now distinguish 2 cases. If the sum of the circulation is different from 0, so we find that the 2 points will rotate one around each. So we have rigid body motion. So the 2 points will rotate around their center of mass with a constant angular velocity, which is this one. Okay, if we take now the sum is 0, what happens in this particular case? They will form a dipole and they will translate, they will travel together. So the 2 points here will travel with constant speed and will move to infinity. And so this is the point vortex. And when we have something for this finite dimensional space, we want to see if we come back to the PDEs now, to Euler equation, if we can find a classical solution with these properties. And this is true. I think I will skip this one because I have no much more time. So we can desingularize. So I can desingularize the Dirac masses into classical solution for Euler equation. And we can desingularize in different ways. Here we can desingularize with patches, but very concentrated patches. And we have different techniques to do that. We have variational techniques, and this was done by Tirkantan in 1985. And with my collaborator, Joan Matteo, we do the same thing, but with another scheme, which is the contour dynamics with patches, which is much more easier and much more direct. And you have different results here. Okay, so I think I have no more time to comment. Okay, now let me move to 4 points. So 4 points, this is in general non-integrable, but when the sum of the circulation is 0, we find integrable system. And to motivate my discussion, I think I need here to share with you this. Yeah. So here we have 4-point vortices, and let's get to look to their motion. So they start to evolve, and they form some symmetric shapes because we start with something symmetric with respect to this horizontal line. So what happens for the top part is reproduced identically on the bottom. So we have essentially 4 particles, but by symmetry we can transform to 2 particles, and the 2 particles will rotate one around the other, and they will translate. So we have a rigid, we have a combination now between 2 mechanisms. We have the rotation; 2 points will rotate one around the other in this translating frame, and they will translate. So we combine rotation and translation, and the dynamics. What we get for the points is non-rigid time periodic solution in the translating frame. Okay, and this was discovered by Love. Okay, here we have some parameters. So if we start, so this is the configuration. We start with 4 points for Dirac masses. They are symmetric with respect to this horizontal axis. And here, this is the distance between the 2 points will be denoted by d1, and you take the midpoint. So we have this line, which is horizontal, and will cross the vertical axis at the midpoint of the 2 Dirac masses. And you have this is d2. And now the circulation will be plus let's say 1 to simplify, 1, 1, minus 1, minus 1. Okay. So the 2 points will rotate. If you focus on the 2 points here, they will rotate one around each other, but they will translate. And the motion is non-periodic motion. And this is the orbit of your points. So if you look for the 2 points here, and this is exactly their orbits in the translating frame. So you find something is not circular motion, this one. This like an elliptic shape, but it's not elliptic. And the 2 points will circulate on the same orbit. And the period, we can compute explicitly the period. From the dynamics of the equation, we can see that this is not rigid body motion. Okay. And we can do some, this is simple exercise. If we can write the dynamics of the 4 points and we transform into 2 points and we can compute many things explicitly. We can compute the period here of this motion, and the period is connected to elliptic functions. You have E and K, which are elliptic functions. So everything can be done in a direct way, like this finite dimension dynamic system in the plane. So it is not very complicated, but we have to suffer a little bit to compute explicitly many things like the period. Okay, so now maybe to motivate more, and I hope that we'll get something, at least to mention our theorem in this direction. So we want to desingularize. So we want to desingularize. And how to desingularize? To desingularize with patches. So we start with the point vortex system, which are Dirac mass. And if you want something to be close to Dirac mass in the patch form, so we have to put a small shape, but with high intensity. So the intensity is 1 over epsilon squared. And the shape is some small domain around this point. The K here is exactly the Dirac masses. So you can't forget something, some shapes. You have different shapes, by another one, and by symmetry. We have to reflect the symmetry of the point vortex system into this ansatz. So you have to reflect. So we can imagine that you have now points, and we desingularize by small patches here. So this is we have something like this, and they are very concentrated. Okay, this is the theorem. So the theorem is recent results with Zina Bassenia and Nadir Masmoudi. And essentially, I will just maybe make a comment of this theorem. So essentially, if we fix 2 parameters, A and B, okay, and B is smaller than and fix Y0, fix 2 parameters A and B is smaller than Y0 over square root of 2. If we there is some epsilon 0, when epsilon is measuring the perturbation, how to desingularize, when the perturbation of Dirac masses. So for any epsilon in this range 0 epsilon square, we can find a counter set type set is not exactly contour set, but it's coming from the same process of contour set by elimination of intersecting different sets. So we can find contour sets embedded in this segment AB, and this contour set is almost full when you shrink epsilon to 0. When your perturbation is going to 0, this contour set will be exactly the total range B minus A. And now what happens if we select psi 0 is the difference between psi 0 here. So the distance between the 2 points, let's say psi 0, this one. So if psi 0 belongs to this contour set, we can find periodic solution to Euler equation in this patch form. So this means that we can find a set of parameters. When you restrict yourself to the set of parameters, we can generate time periodic solutions for Euler equation. And these time periodic solutions, they are not rigid time periodic solutions. So in some sense, what happens for the points for the Dirac mass can be reflected in this desingularization. We can desingularize them, but here with the difference compared to the rigid body motion that we have to select your parameter in some contour set. And this is due to some resonance that we have to deal with during the scheme, how to generate solution. Okay. Maybe so how much so Nabil 2, 3, 5 minutes? I don't know.
Yes, 5 minutes.
Yeah,
Ma-
let me make some comments about the theorem. I think I will not get the time to explain for you how really to generate completely the proof, but to give you some insights how the proof works and the kind of difficulty that we can encounter when we want to move from the rigid periodic motion to the non-rigid periodic motion. But before that, some comments. So the first one that this is an open problem to generate as I said before, Love discovered this leapfrogging phenomena with 4 points many years ago, and it was an open problem to see whether we can find a classical solution around this Dirac mass Euler equation that will reflect the same motion. So can we reflect this leapfrogging motion from the points to the classical solution? So this is the first result in that direction. And our scheme is much more generous. So we devise a scheme, and this scheme does not solve only this problem, but we believe that it can solve many connected problems related to non-rigid periodic solution, because we have many examples of non-rigid periodic solutions coming from the point vortex system. As I said before, the point vortex system is finite dimensional system, and we can track the motion in some specific cases, and we can generate many configurations which are periodic but non-rigid. And now with this approach, we believe that we can at least tackle some of them and desingularize them into classical solutions. Okay, so maybe some comments for those who know this recent result of Davila Del Pino, Mosso and Way for dimension 3. At the beginning of my lecture, I mentioned this ring that they start to leapfrog. So they are animated by this dance. One is slowing down, the other one is accelerating. They will enter one inside the second one. They will reproduce in a perpetual way this dance. And this is still an open problem. And Davila Del Pino also try to explore this, but for short time. So for short time, and they don't really discuss exactly what we can see in this video, but they said essentially we see this one, but plus some perturbation. But this perturbation is a diffusion everywhere, so we don't. It seems that they are not able to remove this perturbation, and we understand why they are not able to remove, because we have different resonances, and we can generate some instability. And if we want to remove all these perturbations, this means that we have to work with resonances and to restrict your parameters. Need to restrict your parameters in order to kill all these resonances parts, but to kill them, we have to track on the way how to generate the solution. So, and the solution is so I think just to move to the final scheme that we have different things. I will share with you these kind of things. So basically, we want in this configuration, the problem and the main enemy is the small divisor problem. And let me say that when we want to generate a solution, how to generate solutions for when we want to for fx is 0. In general, we use contraction principle, or sometimes we can refine this Newtonian scheme, and the appropriate one, which is much more suitable here, is Nash-Moser scheme. So Nash-Moser scheme is like a Newtonian scheme, but we smooth out this scheme in order to deal with some loss of regularity coming from when we generalize, we have some loss of regularity.
رفيق رفيق اسمع
Yes.
Donc
Maybe
Taoufik s'est
Taoufik.
déconnecté, hein?
Yes, he has a problem.
Okay, but we can wait some minutes.
Yes.
Let him join us. Perhaps he has a problem with
Sorry.
his connection.